So sometimes when we're working through these L'Hopital problems and we plug in, we get other forms besides 0 over 0 or infinity over infinity plus or minus. So what happens? What are those other forms that you might get? You might get something like 0 times infinity. You could get something like infinity minus infinity. You could have 0 raised to the 0 power. Shoot, you could even have infinity raised to the infinity power, 1 raised to the infinity power, and then plus or minus infinity times 0, whatever, right? So a lot of different forms that you could get whenever you plug in. So what do you do when you see one of these situations here? Well, you're going to use algebra tricks, not ticks. Okay, tricks to rewrite as, well, what is the form that we need it to be in order to use L'Hopital? It needs to either be in 0 over 0 or infinity over infinity plus or minus, right? So once you get it in this form, then all you got to do is L'Hopital it. Okay? So here's an example of what I'm talking about. Limit as x goes to 0 from the right, remember the plus means to go from the right, of x ln x, okay? So whenever I plug in to see what type of form that I have, I plug in 0, I have 0, positive 0, and then natural log of positive 0. So what is positive 0? That's 0, right? Times a natural log of 0. So if I'm on the positive side, where's this going down to? It looks like it's going down to negative infinity down here. So this is like negative infinity times 0. So that's the form. Can I use L'Hopital in this form here? No, I cannot. Okay? So I can't use L'Hopital here, so I'm going to have to use some algebra trickery in order to rewrite this in the form of 0 over 0 or infinity over infinity, whichever one works. Okay? So when I can avoid it, I don't like to move this one to the denominator, because taking the derivative of 1 over natural log x is a lot harder than taking the derivative of natural log x. And whenever I look at the other thing I can change, I could rewrite this x, I could rewrite that so that I have a limit as x goes to 0 from the right of ln x divided by 1 over x. Okay? Now you'll see if you use your keep, change, flip rule, remember keep, change, flip, right? You keep the numerator as ln x, change division to multiplication, and then flip the denominator. When you flip 1 over x, you get x. Okay, so that gets you back to where you started, right? So algebraically, this is my algebra trick. To get this in the denominator, I just write the reciprocal in the denominator. Okay, so that's what I did there. Now, I check the form, see what the form is. The form, well, the numerator's still the same, so I still have that positive or that negative infinity in the numerator. Now, 1 over something really close to 0, 1 over something small is equal to something big, right? So this is a positive infinity here. So my form is infinity over infinity. So now I can use L'Hopital. So I'm going to take L'Hopital here. Limit as x goes to 0 from the right. The derivative of ln x is 1 over x. The derivative of 1 over x, well, let's convert this to make it easier. That's x to the negative 1. The derivative is negative 1, x to the negative 2. Simplify, so that's negative 1 over x squared, right? Okay, now I have a fraction divided by a fraction. So I'm going to keep, change, flip this bad boy. And so what do I get? I get the limit as x goes to 0 from the right of keep the numerator the same, change division to multiplication, and then flip the fraction in the denominator, right? Okay, so now what do I get? Simplified, this is going to get me x squared over negative x. And so the x's cancel, right? And so I have 2 x's in the numerator, 1 x in the denominator. So as x goes to 0 from the right of negative x, okay, what does that equal? Well, that's just negative 0, which is equal to 0, okay? So my answer here is 0. All right. Now, for my next trick, I'm going to have the limit as x goes to 0 from the right of 1 over x minus 1 over sine x. Okay. And so what I'm going to do here is I'm going to do form. So let's do green. I like green. Form. Plug in. So 1 over 0 positive minus 1 over sine of 0 positive. Okay. 1 over 0 positive, that's something, 1 over something very small and positive is positive infinity. Now, what about sine of x? How does it behave as we're approaching 0 from the right? It's positive, but it's small positive. So it's minusing a very big positive number, okay? So I have infinity minus infinity is my form. Is that L'Hopital ready? No, it is not. How can I combine these to potentially make it L'Hopital ready? Well, what I can do is I can get a common denominator, all right? So let's do that. Let's get a common denominator. How do we do that with 2 fractions? In order to add 2 fractions, what do you need to have? Well, you got to have a common denominator. So I'm going to multiply through. I'm going to multiply through. And let's see here. I need, oh, that's not what I want to do. I need a sine x over here, and I need an x over here. So whenever I do that, what do I get? Get the limit as x goes to 0 from the right of sine x over x times sine x, that's my common denominator, minus x over x times sine x. Now that I have a common denominator, what can I do? I can combine the two. And so I have sine x minus x divided by x times sine x. Okay? So you're getting common denominator here. All right, the least common denominator is sine x times x. All right. So now I check the form. So what is the form? Whenever I plug in, what do I get? Well, I get sine of positive 0 minus positive 0 over positive 0 times sine of positive 0. So that's sine of positive 0 is 0 minus 0 over 0 times 0. So that's 0 over 0 is my form. So I'm ready to L'Hopital this thing, okay? So I'm going to L'Hopital here. If I L'Hopital, the derivative of the numerator, sine x is cosine x. Derivative here, minus 1, okay? Now the denominator, it's a product of 2 functions, the first and the second function. So to find the derivative using the product rule, first times the derivative of the second plus the second times the derivative of the first. Okay. So now I'm going to, well, I guess I could just plug in and see what happens, right? So if I plug in, what do I get? Well, I'm going to get cosine 0 minus 1 over 0 times cosine 0 plus sine 0 times 1. So that's 1 minus 1 over 0 times 1 plus 0 times 1, right? Okay, so that's just 0 over 0 again. So I'm going to have to use L'Hopital's rule again here. Oh my gosh. L'Hopital's rule again. Yikes. So the numerator is not too bad. That's negative sine x. The denominator is a booger. I got to use a product rule here, and then I just need to take the derivative there because 1 is just, that goes away. Okay? So using the product rule, first times the derivative of the second plus the second cosine x times the derivative of the first. Okay, that takes care of that part. Now the derivative of sine x is just cosine x. Okay. All right, now I'm going to plug in 0 and just see what I get. Hopefully we're done with this, right? So that's going to be negative sine of 0 in the numerator, and 0 times negative sine 0 plus cosine 0 times 1 plus cosine 0. So sine of 0 is 0, but in the denominator, this gets you 0, but this gets you 1, and this gets you 1. So that's 0 over 2, which is equal to 0. So holy smokes, we got an answer. So my answer here for this limit is equal to 0 here. Okay? So that one was kind of tough, all right? That one was kind of tough, but we were able to hang in there and handle it just fine. Okay? Let's try another one. Limit as x goes to 0 from the right of x raised to the sine x. Seems like a good test question. All right. This one here, when I look at the form, all right, this should remind you of something similar to like a super exponential. Not only is the base changing, but the exponent is changing as well. So this one is pretty tough. Okay, pretty tough problem. Now, when I plug in 0 for x, I get 0. I plug in sine of 0, I get 0 there. So this is the form 0 raised to the 0 power. This is an indeterminate form. If I have this type of situation coming into play, I have something raised to some other power, we have to use our ln trick. Okay, so how does this work? So here's how we solve this type of problem. I'm going to let y equal this limit. The limit as x goes to 0 from the right of x raised to the sine of x. Okay, so I'll let y equal that. Now what am I going to do to y? I'm going to natural log y. Okay, and so that means I'm going to natural log the limit. So when I natural log, why am I natural logging here? Well, the natural log rule tells me that whatever's to the exponent comes out front, right? So whatever's in the exponent is going to come out front. So this becomes the limit as x goes to 0 from the right of sine x multiplied by the natural log of x. Okay, remember that exponent comes out front, the power rule. That's why we use log to bring the exponent down to the level where we can work with it. Now look at the form. What's the form here? Can we use L'Hopital? Well, sine of 0 is 0. And ln of 0 from the right is negative infinity. So we know how to handle this form, okay? We don't like to do the reciprocal of natural log, so that means that leaves us doing the reciprocal of sine x. And so when we do that, what do we get? get the limit as x goes to 0 from the right of ln x in the numerator, but in the denominator it's 1 over sine x. Now 1 over sine x can be written using a trig identity known as cosecant x. Okay, so 1 over sine is cosecant. Now, whenever I plug in 0 here, I get in the numerator, what is it? It's of the form negative infinity over, and then this is a positive infinity here. 1 over a really small positive number is positive infinity. So infinity over infinity is L'Hopital form, so I'm ready to take the derivative here to get it. So let's take the derivative. Limit as x goes to 0 from the right, 1 over x for ln x. And then the derivative of cosecant is negative cosecant x cotangent x. Okay? What a mess, right? Whew, man. Nasty mess right there. Okay. I'm going to use some algebra to simplify this, make my life a little bit better, because instead of working with cosecants and cotangents, I want to work with sines and tangents. So I'm going to flip this around. Limit as x goes to 0 from the right, and I'm going to use algebra to flip this around. Remember, keep, change, flip, right? So keep, change, flip. But this can flip again. This can turn into sine x times tangent x using your trig identities. Okay, that's what this part equals here. All right. And so this is going to be what? It's going to be sine x, tangent x in the numerator, and then the denominator just x. Okay. So when I plug in 0, what do I get? Sine of 0 times tangent 0 over 0. That's 0 over 0, so I'm going to L'Hopital. When I L'Hopital, the denominator is 1, but the numerator, I've got to use the product rule. First times the derivative of second, plus the second times the derivative of the first. Okay? And when I plug in 0, what do I get? I get 0 and then 1 squared plus 0 and 1 over 1. So that's 0 over 1, which is 0. Okay? So my answer there is 0. But do not let this fool you, because here's the thing that messes students up. They think, man, I did all this work and I got 0. I must be done, right? But what did you do? You did the natural log of the answer. So the natural log of the answer is equal to 0. So what does that mean? So I need you to write this, okay? So that says if the natural log of the answer is equal to 0, then what does that tell me? To get back to the answer, I got to do e to the ln y equals e to the 0. Why did I do the e's? Because remember, e and ln are the inverse of each other. So now that tells me y is equal to e to the 0, which is 1. So what does that say? Well, y is the limit as x goes to 0 from the right of x to the sine x, which is equal to 1 now. Okay? So very important. This is the last step, and this is the step that people forget. So don't be that person that forgets this step right here. All right? You do all that beautiful work, you get to right here and you say the answer is 0. Oh man, you missed it because the answer was 1, right? So don't be that person. All right? We got one more of these. This is a very special limit. Limit as x goes to infinity of 1 plus 1 over x raised to the x. Okay? Now, what is the form? What is the form here? So the form is 1 raised to, well, how do I know it's 1? Well, I plug in 1 plus 1 over infinity raised to the infinity. So 1 over infinity, that's going to 0, right? So this is 1 raised to the infinity. All right, so 1 to the infinity. When I see something to the infinity power, I'm thinking use my natural log trick. So first thing I do is say y equals limit x goes to infinity, 1 plus 1 over x, raised to the x there. Okay. Now that I've done that, what do? I natural log both sides. So I'm going to ln this side. That means I'm going to ln this side over here. So I have the natural log of y is equal to the limit as x goes to infinity of ln 1 plus 1 over x raised to the x power. What do I know to the exponent? The whole reason I log it is so that I use the power rule and bring the x out front here. So the x comes out front here. Now I'll look at my limit. What's the form? Is it in L'Hopital form? Well, it's infinity times the natural log of 1 plus 1 over infinity. So that's infinity times the natural log of 1 plus 0. So that's infinity times 0. So I'm not in the form yet, okay? But I have multiplication of two things together, so I'm going to do a reciprocal one. I want to avoid doing the reciprocal log, so I'm going to do the reciprocal of the x here. So algebra trickery to get it to limit as x goes to infinity of ln 1 plus 1 over x over 1 divided by x here. Okay. Excuse me. So now when I check the form, once again, this form here that ends up getting me ln 1 plus 0 over 1 over infinity. So 0 over 0 form, I'm ready to use L'Hopital. So I'm going to use L'Hopital. Limit x goes to infinity. If there's one thing you take away from this video, by golly, you do not use L'Hopital until you get a form 0 over 0 or infinity over infinity. That is very important that you understand what you got to do there to get the right answer. Okay, so off the soapbox. All right, need to take the derivative of this nasty thing right here. Oh my gosh. So remember, with a natural log, I just write whatever's in the argument in the denominator. Okay, and then I take the derivative of the denominator. So I take the derivative of the denominator. That's derivative of 1 is 0. Derivative of 1 over x is negative 1 over x squared. Okay. And then divide by 1 over x derivative, which is negative 1 over x squared. Okay. Hey, this is going to work out nicely. Let's do some algebra to simplify. Limit as x goes to infinity. This is 1 over, if I combine this, I'm going to get x plus 1 over x. And then this is going to be negative 1 over x squared. There's a reason I'm not simplifying this quite yet. And I think you're going to see why I didn't simplify it yet. Because what can I do here? These two factors look like they're going to cancel each other, right? So what does that get me? That gets me the limit as x goes to infinity of 1 over x plus 1 divided by x. Okay. So let's take the limit. Actually, why not simplify it a little bit more? Keep, change, flip. Keep the numerator same, change division to multiply, flip the denominator. So I just get x over x plus 1. And the limit here is 1. Okay. degree in the numerator and the denominator are both 1, so I look at the coefficients, and since there's no number there, it's understood that they're both 1, so 1 divided by 1 gets you 1. Okay? Now, is 1 the final answer? No. Why not? Because we natural logged. So how do I get back to the right answer? Well, I take my answer, my ln of the answer, and I e both sides. If I e both sides, what happens? I get y equals e to the 1. So that means the limit as x goes to infinity of 1 plus 1 over x raised to the x is equal to e. Whoa, very cool, very cool. And some textbooks actually use this as the definition of the exponential base that's so very important, e. Okay, that number, e. So this is a way to calculate e through an infinite limit. Pretty awesome there. Okay, so if you were, in a bind and you had to figure out a good approximation for e, you just pick a big number to plug in for x, and then you could get a rough approximation. All right, good luck calculating it, but you could if you had to. All right, guys, let you digest this, and then I'll do a summary video of all the different forms of limits, and maybe that will help you out.